Listen, if you walk into your Cambridge IGCSE Computer Science 0478 exam and just write, "A hub connects computers," you're instantly throwing away easy marks. You're putting your grade boundaries at serious risk, and we definitely don't want that. So today, I'm giving you a zero-fluff, hyper-focused guide to totally mastering network devices. We aren't just going to memorize basic definitions here. We're going to deeply understand the actual mechanisms so you can construct those exact high-band answers that examiners are absolutely desperate to see. No wasted time, just the pure actionable knowledge you need to ace this syllabus.
Okay, let's dive into this. Notice the weak answer on the left. A hub connects computers. I mean, sure, it sounds true, right? But to an examiner, it's vague, it's generic, and it scores exactly 0 marks. Because it doesn't prove you actually understand the underlying computer science. Now check out the top band response. A switch limits broadcast traffic by creating point-to-point connections. That is absolute music to an examiner's ears. It uses precise technical vocabulary, it clearly explains the mechanism, and boom, it secures full marks. The stakes are exactly this high, guys. Ordinary revision fails because it stops at basic definitions. Today, we are completely upgrading your technical language. So, the crucial first step is understanding the environment where these devices actually live. Let's define our playing field, starting with the physical scope. A local area network, or LAN, is what you typically find in a home or a standard office. You've got wireless routers with built-in modems, hubs, and switches broadcasting a LAN so that computers in that immediate area can join. Now, broadcasting distance definitely varies, but a LAN generally spans around 300 feet, which is roughly 91.44 meters or slightly more. Any computer on this network can share connected resources, like a high-speed internet connection or shared printer down the hall.
But what happens when we need to scale up our network? Well, that's when we introduce the Metropolitan Area Network, or MAN. And it's exactly what it sounds like. It connects 2 or more local area networks or campus area networks together. However, the strict rule here is that a MAN does not extend beyond the borders of an immediate town or city. To build this larger metropolitan network, we essentially have to start connecting routers, switches, and hubs together to bridge all those individual LANs.
Finally, we scale all the way up to the largest category, the Wide Area Network, or WAN. A WAN covers a truly massive geographic area. We're talking about data communications crossing metropolitan, regional, or even national boundaries. It's moving data from city to city, or literally moving it internationally across the globe. Unlike those smaller LANs we talked about, which usually just sit in a single room or building, WANs rely heavily on routers and public communications links. And, as you might have guessed, the absolute largest and most famous example of a WAN is the Internet itself.
And this brilliantly illustrates the complete taxonomy of network scales. Just take a second to absorb how this all builds up, from a single room all the way to a massive global system. You've got your LAN in a building relying on hubs and switches, your MAN spanning a whole city, and your WAN utilizing powerful routers and public links to cross entire regions. Grasping this geographic scope is your foundational step. Now that we have the scale perfectly mapped out, we really need to dive into the core mechanisms that make these different devices tick.
Section 1. Broadcast versus point-to-point, the core mechanism.
Right. This is where we separate the basic students from the top-tier candidates. We're moving away from just what the devices are, and we're diving deep into how they function internally. Let's look at the humble hub. A hub basically operates on a broadcast network principle. Imagine some guy standing in a silent library with a megaphone. That's exactly what a hub is doing. Here is the mechanism. Step 1. Data enters from a source machine. Step 2. The hub literally lacks the intelligence to know exactly who that data is meant for, so it simply duplicates it. Step 3. It blasts that information to all connected devices simultaneously. Now, this broadcast method is perfectly fine for simple announcements in a really small local area network. But as networks grow, this simplicity becomes a massive, massive liability.
Because a hub is literally shouting every single piece of data to every connected machine, it faces some really severe challenges in larger, more complex environments. The source material highlights a few absolutely critical weaknesses here. First off, you get terrible network congestion because the lines are just flooded with irrelevant data. This can rapidly escalate into what's known as a broadcast storm, where the network essentially gets so overwhelmed it just grinds to a halt. You also hit hard scalability limits. You simply can't add many devices before the noise becomes totally unmanageable. And finally, think about the security risks. If every single device receives every data packet, intercepting sensitive information becomes frighteningly easy.
So, to solve these massive issues, we bring in switches and routers. These devices are much smarter.
They operate on a point-to-point network model. When a packet of data enters a switch or a router, it doesn't just blindly copy and shout it out. Instead, the device actually identifies the specific destination. To get from the source to the destination, the packet is sent on a dedicated point-to-point connection, strictly between that individual pair of machines. By doing this, switches and routers actively segment the network. They limit that messy broadcast traffic, completely sidestepping the congestion and security flaws of a basic hub.
Now, in a moment, I'll show you the exact examiner clue regarding network congestion that changes your answer entirely. But first, you need the framework that makes this clue obvious. You see, understanding the mechanism is really only half the battle. If you don't know how to structure that knowledge into the exact answer that the Cambridge mark scheme demands, you're still going to lose points.
Section 2. Perfecting your exam answer. The examiner framework.
To extract maximum marks, we have to totally shift our mindsets. Stop acting like a student just trying to remember facts and start acting like an elite exam hacker who knows exactly how to pull maximum points from every single question. The IGCSE syllabus is incredibly strict about command words. If a question asks you to state or define, they just want a concise technical fact, nothing more. If they say describe, you need to give the actual characteristics of the device. But if they say explain, which is where the big, juicy marks live, you absolutely must give the why and the how. And remember this golden rule: 1 mark usually needs 1 distinct technical point. A huge mistake students make is writing a massive paragraph that just repeats the exact same technical point in 3 different ways. That is only ever going to score you 1 mark.
So, to guarantee you hit multiple distinct points, you need to use this ultimate answer template for your explanation questions. Step 1, start with the definition of the device. Step 2, state its core mechanism. Is it broadcast or point-to-point? Step 3, apply it strictly to the scenario example given in the prompt. For instance, if they mention a hospital, your answer absolutely must talk about the hospital's data. Step 4, state the consequence or the specific advantage of that mechanism. And Step 5, wrap it all up with precise examiner wording, like limits broadcast traffic.
All right, let's test this right now. Here's a classic high-mark exam question. Explain why a switch is preferred over a hub for a large corporate LAN. I want you to pause this explainer right now. Nope, seriously, pause it. Try to mentally build your answer using that 5-step framework we just covered. Make sure you include distinct technical points about the mechanisms and the consequences. Go ahead, I'll wait. Okay, let's see how you did. If you were peeking at the examiner's actual mark scheme, these are the exact distinct technical points they are hunting for. You get a mark for mentioning that a switch segments the network. You get another mark for stating it creates point-to-point connections. Another mark for noting it limits broadcast traffic, which directly prevents those nasty broadcast storms. And finally, you can easily grab a mark by explaining it improves security because the data isn't just disseminated to all connected devices simultaneously. Every single one of these is a distinct, measurable point. Now, what's really interesting about this slide is how we upgrade a genuinely flawed student answer into a top-band masterpiece. Look at the left side. It simply says switches are faster and safer. A student might actually think this is a pretty good answer, but it totally lacks technical depth. It doesn't explain why. Now look at the right side, which uses our framework. A switch creates point-to-point connections, limiting broadcast traffic and preventing broadcast storms, which improves security. Do you see how it beautifully strings together the mechanism, the consequence, and the specific examiner vocabulary? That right there is how you secure full marks every single time.
So, you now have the ultimate framework for handling hubs and switches within a local area network. You know exactly how to avoid the broadcast storm trap and secure those juicy mechanism marks. But here is the big unresolved problem. What happens when the exam scenario pushes you way past the boundaries of a single building? What happens when your local network needs to connect securely to a database across the globe, crossing into wide area networks and public communications links, all while maintaining absolute data integrity?
Because if you try to answer a massive global network question using only LAN principles, your answer will just shatter under examiner scrutiny. Mastering those local devices was just step 1. Your mandatory next step to completely finalize your exam strategy is to watch our Computer Science 0478 Last 7 Days Revision Map explainer right now. That is exactly where we take these local mechanisms and tie them into the complex global protocols that the syllabus absolutely demands you understand for those really tough paper questions.
So, when you finally sit down for that exam, are you going to let your grade get lost in a chaotic broadcast storm, or are you going to build a secure point-to-point path straight to full marks? Do not let your revision stop halfway. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to totally master these frameworks. Click the next explainer on your screen right now and let's lock in those top grades. See you there.